Now, welcome back. So basically where I left off with you guys is that we worked out the area under a curve from A to B, the curve being y is equal to f of x, and we worked it out basically by using the sandwich technique. Remember that? So basically what we did was we cut up the curve into little strips of width dx, which the limit of which approached 0, and basically as the limit approaches 0, the sum of the upper strips and the sum of the lower strips will sandwich into the actual area under the curve. Does that make sense? And the formula is basically the limit of d of x approaching 0 for the sum from A to B of f of x times d of x, right? And we worked out that, and I basically left you off with the fact that when we're doing calculus, when we're doing integration, we don't write it like this. There's a more efficient way of writing it, which is integral notation, which ends up looking like this, right? But it actually is the same thing, right? But what I want to do now is, now that we've worked out a way of writing it, how do we solve it? How do we solve it from here? So what does this give us, right? And this is what I want to do. Basically, I want to consider that there is a rule that this becomes. It's going to become a rule, and let's call that rule another function, right? The rule is going to be the function a of x, a for area, right? A of x for the area under y is equal to f of x from x equals to a to x. So we're finding the area from A to another point x, right? So basically, here's where I want to start things off. We worked out the area of one of these strips, right? We worked out that the area of one of these strips is going to be between f of x times d of x and f of x plus d of x times d of x, right? So let's start with one of these strips. The area for one of these strips is going to be f of x d of x, somewhere between that, and also it's going to be f of x plus d of x d of x. Now, if we need to kind of refresh why that is the case, we go here. So it's going to be the area of the lower rectangle on one end of the inequality and the area of the upper rectangle with the red tip over on that side. And that's going to be the area of one of these strips, right? Now, remember how we said that the area is going to be a of x? That's the rule for the area. Well, the rule for the area is going to be, for the rule for one of these strips is going to be area of the red bit minus the area of the black bit. So what's going on here? To find the area of one of these strips, we are going to find the area of this strip and minus the area of this bit. Does that make sense? So what we've got here is that the area of one of these strips is going to be a of x plus dx minus a of x. So this strip here is going to be this strip minus this strip. Okay? So that's what's going on. Now, I'm going to do something sneaky here, right? What I'm going to do is I'm going to divide everything by dx. So let's do that. If I divide everything by dx, I end up with f of x on this side, and I end up with, let's say, I'm going to keep it black now, a of x plus dx on this side, minus a of x all over dx, which is less than f of x plus dx, which is less than f of x plus dx. Does that make sense? Good. Now, do you remember what the limit of d of x was? What was the limit of d of x? The limit of d of x was d of x approaching 0, yes? So that's what we're going to be doing, right? Now, as let's do this. So you got limit of x d of x approaches 0 for f of x is less than the limit of d of x approaching 0 for a x plus dx minus a of x dx, which is less than f of limit d of x approaches 0 for f of x plus d of x. Does that make sense? All right. So basically what we're doing is we're applying the limit of what we did over here, which is basically what we need to do to sandwich it in and work out the actual area, okay? So the limit of d of x approaching 0, well, there's no d of x in f of x, so it's just going to be equal to f of x. And when d of x approaches 0, what's happening here? It's just going to be equal to f of x, right? So this is going to be equal to f of x. This is going to be equal to f of x. And this is going to be equal to, right, limit d of x approaches 0 of a of x plus dx minus a of x over dx. Now, here's what I want to do with you. Where have you seen this before? Have you seen this before? Let me give you a bit of a hint. Do you notice a similarity between this and this? Yep. Now, where have you seen this before? Yeah? This is differentiation by first principles, yes? This is also differentiation by first principles. It's exactly the same thing. You've just used different notation. You've just used different letters to show exactly the same thing. Does that make sense? All right. So in other words, let me just use this side of the board now. What we've got, while this is basically f dash of x is equal to the limit of h approaches 0, f of x plus h minus f of x over h, while that's equal to that, what you've got over here is you've got this bit here equaling f of x. So you've got f of x equaling the limit of d of x approaching 0 for a of x plus d of x minus a of x all over d of x. Okay? Now, basically, what you've got is that what this basically means is that the derivative of a of x is equal to f of x, right? That's essentially what it means. The derivative of a of x, this rule here, is going to be this rule here, which actually means that to find the rule a of x, it's going to be, what's the opposite of differentiation? It's going to be the anti-differentiation or the primitive. So the primitive of f of x is f of x plus c. All right? That's really what's going on here. The rule to find the derivative, or the rule to find the area under the curve is actually the antiderivative of the function. In other words, what that's saying is integration, finding the area under the curve, is exactly the opposite of differentiation, which is finding the gradient function of the curve. They're actually opposite signs of each other, like multiplication is the opposite of division, and division is the opposite of multiplication. So that's basically what's going on. Okay, cool. So from here, basically, we've got to work out what your C is, right? So A of A is equal to 0, which means F of A plus C is equal to 0. So basically we're putting F of A equal to 0. Now, that means that C is equal to minus F of A, and A of B is equal to F of B. So in other words, the primitive function with B substituted into it plus C. And we know that C is F of A. So F of B minus F of A, which is the area from A to B. So the area from A to B, so the area from A, the area under y equals to f of x from x equals to A to x equals to B is going to be that f of B minus f of A. And what is that? What's another way of writing that? Well, it's this over here, right? So it's going to be area A to B of f of x dx is going to be your area. And that is basically what we call the fundamental theorem of calculus. What essentially it means is that in order to find the area under a curve, right, you find the primitive of the function, right, substitute the limits, which is your a and b, and that'll give you the area under a curve. Great. Okay, so now all of this stuff, you might be thinking, watching this going, wow, this is just way too much. I'm way in over my head. For others of you, you're going, wow, this is cool. I really like this. Whatever your situation is, this is basically just showing you how integration works and how integration is related to differentiation. You don't need to memorize any of this stuff. It's just there to kind of set up the foundations for the rest of the work that you're doing. If you don't fully understand it, it's totally okay, right? But for those who do understand it and are extended by it and have gotten something out of it, then this will really deepen your understanding of the why of calculus or the how of calculus, and not just the mere application of it. Okay, so good. Thank you very much for watching. I'll see you on the next episode. I thank you again for your patience.